All right, let's look at 2.3, where we consider a space of bounded functions. And in fact, we'll have our first example of an infinite dimensional normed linear space. We won't establish that in this very brief little section. It's left as one of the homework exercises. So what we'll do is start with the arbitrary set, capital S. We had introduced the notation a few sections ago that capital F of set S is a set of all functions f, mapping the set into the real numbers. So the domain of such a function, lowercase f, is the set, capital S, and the codomain is the real numbers. So the function values are real numbers, and we know a lot of stuff about real numbers, so we can have a moderately concrete conversation about the outputs from such functions. A definition for such a function, f, in this collection of all functions mapping set S into the real numbers, define the, we'll call it the suit norm, define the suit norm of f to be the supremum of the absolute value of f of s as the input to that function, lowercase s, ranges over the whole set. All right, as the input ranges over set capital S, the f of s values, it's a collection of real numbers. We'll take the absolute value of that. We can do that for real numbers. So we're simply taking the supremum of a set of real numbers. A set of real numbers always has a supremum. It might be infinity, and we'll discuss that here shortly as well, but supremums of sets of real numbers can certainly be infinity. This is called the suit norm. Now, I certainly owe you some details to establish that really is a norm. We'll need a very specific setting to deal with that acting as a norm, and that setting is the following. We'll define the set of all bounded functions on S as the bounded functions on set S, B of S, is the functions in this capital F of S such that the norm is finite. The norm is a sup, as I mentioned, it could be infinite. So we're looking at bounded functions. Their biggest value is finite, and that's an awkward way to say it, arguably an inaccurate way to say it. But these functions are bounded. There's some bound, actually there's what it is. Exactly, it's the norm of the function. That's the least upper bound of the function values. It's a supremum of the function values. So these functions are definitely bounded. The outputs are real numbers, and boundedness makes sense. And our one claim from this section is this collection, B of S, is a normed linear space. Okay, so two things to show. It's a norm. The suit norm actually is a norm, and the suit norm is defined on a linear space. Okay, we'll kind of weave those two ideas together. First, take a couple of functions, f and g, to be from this bounded collection of functions, B of S. For any lowercase s, an element of set capital S, we have f plus g of s is f of s plus g of s, absolute value of on both sides. Very definition of adding two functions together and then evaluating them at a particular point. All right, so here we have, for a given value, lowercase s, we've got a sum of two real numbers. So like I said, we're getting outputs that are real numbers, and we know lots of stuff about real numbers. Let's just use the triangle inequality on that. Triangle inequality from the setting of the real numbers. Simply have this real number plus that real number in absolute value, less than or equal to the absolute value of the first plus the absolute value of the second. Triangle inequality on R. Now, if we wanted to compute the supremum of function f, we'd take the sup of all values as s ranges over set capital S, absolute value of f of s. So we're guaranteed that the supremum is greater than or equal to any particular absolute value of f of s, and the same goes for the g function. F and g got into this B of S collection by having finite norms. That's finite and that's finite, so the sum is finite. Now, what we're going to do is make a transition from the fact that f plus g of s in absolute value is bounded by this norm plus that norm for all s in set capital S, to taking a supremum of this quantity. If we take a supremum as s ranges over set capital S, that'll produce the norm of this. For all s, we have this upper bound, so the supremum, that is the norm, will also have that same upper bound, norm of f plus norm of g. So we've accomplished two things in this. We've accomplished that this sup norm thing on this collection of functions satisfies a triangle inequality, as it must if it's actually a norm. And we've shown that f plus g is also a bounded function. Its norm is bounded by the sum of the norm of f and the norm of g. Both of those are finite, so this norm is finite as well. That is, f plus g is a bounded function. We're trying to show really two things. We're trying to show B of S is a normed space and B of S is a linear space. This takes care of the triangle inequality part on the norm, and this takes care of closure under vector addition. Think of the functions as vectors. So we've got closure under vector addition. To have a normed linear space, on the linear space part, we needed closure under linear combinations. Now we're halfway there. We got the vector addition part left. Let's look at the scalar multiplication part. So take alpha to be a scalar, a real scalar. In this case, we've got real valued outputs. So the scalars are real. And let f be an element of the B of S collection. The absolute value of alpha, f of s, is absolute value of alpha times absolute value of f of s, just the absolute value of a product of two real numbers, s being given from above, so considering for now a fixed s. We'll do some soup stuff here shortly. So if we look at the norm of alpha of f, that'd be the supremum of the absolute value of alpha f of s as s ranges over the whole set, capital S, definition of norm, the sup norm. And we just saw that the absolute value of alpha f of s is the same as the absolute value of alpha times the absolute value of f of s. We're in a familiar setting, the real numbers, because the function values are real numbers. So we get this behavior. We've got the sup of a constant times this, and can bring that constant alpha outside of the supremum. We get an equality as long as alpha is non-negative. It's the absolute value, sorry. As long as the absolute value of alpha is non-negative, and it is because it's an absolute value. With the absolute value not there, this becomes more complicated. But we can bring this non-negative constant out front of a sup. Then we've got a supremum of the absolute value of f of s, s ranging over set capital S. Well, that's simply the norm. So we get the absolute value of alpha times the norm of f. And this was, we called it the scalar property. So the sup norm satisfies the scalar property. The norm of alpha f equals the absolute value of alpha times the norm of f. So there's a second part on the definition of a norm. And there's the second part on the linear space as well. So if we take f to be an element of this collection, B of S, a bounded function on set S, then a scalar multiple of it is also bounded. The norm of f is bounded, then the norm of alpha f is also bounded. That is, alpha f is an element of B of S. So we've shown for f and g, elements of B of S, their sum, vector sum, is in B of S. For f and B of S and alpha scalar, the scalar multiple, alpha f is in B of S. So we've got this collection B of S closed under the two things you do in a linear space, adding vectors together and multiplying them by scalars. In other words, if we take any scalars alpha and beta and any f and g in B of S, the linear combination is in B of S, to be more specific. So B of S is a linear space. So we've got linear space as requested. Norm, we're not entirely done with the norm. There were three properties. We've got the triangle inequality on the norm, and we've got the scalar property on the norm. Next slide. To show this actually is a norm, we needed the triangle inequality, we needed the scalar property, and the third property was if the norm equals 0, then the function is the 0 vector. If the norm of f equals 0, then by definition the supremum of the absolute value of f of s, as s ranges over set capital S, that sup of absolute values is 0. Well, it's absolute values. All of these are non-negative. If the sup is 0, they all 0. So all of these f of s absolute values are 0. That is, the function is identically equal to 0. So it's the 0 vector, if you like. So the norm properties are satisfied as well. And this sup norm thing really is a norm on this linear space. And B of S, as claimed, is a normed linear space, and it's normed under this sup norm idea. In exercise 1.8 of this chapter, it's to be shown that B of S under the sup norm is infinite dimensional when S is infinite. When S is finite, it turns out it's isomorphic to Rn if n is a cardinality of set S. But when it's infinite, we're dealing with an infinite dimensional vector space. So there's our first example, and not our last, of an infinite dimensional vector space. One other little comment about this sup norm thing. If we have a sequence of functions, a sequence of vectors, f sub n converging to f in this normed linear space, B of S, then by definition, for all epsilon greater than 0, there's a natural number capital N such that when the index lowercase n is sufficiently large, that is greater than or equal to capital N, we have the norm of f sub n minus f less than epsilon. Straight up definition of convergence of a sequence. Really the same definition you had in calculus 2 for convergence of a sequence of real numbers. Except here we've got these elements of the B of S normed linear space, and we're measuring distance with a norm instead of absolute value. Other than that, it's exactly the same stuff from calculus 2. Now, when we talk about the norm of f sub n minus f, that's actually the supremum, by definition of the norm we're using here, the supremum of the absolute value of f sub n of s minus f of s, as s ranges over set capital S. So, if we have this convergence, what we're saying is for all values of the index sufficiently large, greater than or equal to capital N, we have f sub n of s minus f of s in absolute value less than epsilon for all elements of that set. Well, that's uniform convergence. So what we're getting here when we do this sup norm convergence in this space is uniform convergence. So convergence under the sup norm implies uniform convergence. So there's something you're probably somewhat familiar with in terms of convergence of sequences of functions. And that takes care of section 2.3. I told you it was brief. We'll move on to 2.4 next time and start looking at more bounded stuff. We'll look at bounded operators in the next section. I will see you there. Bye-bye.